Hi students, I welcome to all of you to this session of fluid machinery. Myself Dhiraj Mondol, Assistant Professor JS College of Engineering. Today I am going to discuss about the numerical analysis on radial flow reaction turbine. Okay, numerical analysis on radial flow reaction turbine. So you know that problem number 14 it is given to you for solving the numerical. Near about 40 to 50% student solve the numerical, and rest of the student you have got some problem, I think. So today I am going to discuss then two numerical on the radial flow reaction turbine. So let us start. Dear students, you can see in the first go through the problem, then solve it, and then pause the video, then solve it yourself. If you get the solve, you can solve the problem, then okay, then see the next rest of the part. And if you can't solve the problem, again it's okay, you just see whatever the solution I am giving you. Okay, in inert flow reaction turbine, the turbine has the external diameter. The external diameter is given, d1 is given. You know that external diameter means inward flow. That means the water is coming from outward to inward like this. And this diameter, external diameter is given. This is your radius r1, so diameter is given, and this is your r2. And outer diameter also given 0.5 meter respectively. The velocity of flow through the runner is constant. Velocity of flow through the runner, that means Vf1 is equal to Vf2, we know, in case of radial flow reaction turbine. So that is your 1.5 meter per second. Determine discharge through the runner. Discharge through the runner and width of the turbine at outlet. If the width of the turbine at inlet is your, so width at that of the turbine at inlet is your 200 mm, that is your 0.2 meter. We have to take in terms of SI unit. You have to calculate the B2 and also discharge. And discharge, we know that discharge is equal to area into velocity. So if you are taking area A1, then velocity F1. Okay. So area is pi D1 into B1 into Vf1. But as you know that all the values are not given in case of your outlet. So A1 is given, B your area is basically area. How you can find out the area? Area is equal to pi D1 into B1, and D1 is given, B1 is given, so you can find out the area. Now velocity of flow also given, so simply find out the put the value, you will be getting the answer 0.9425 meter cube per second. Now you know that continuity equation, Q is equal to area into velocity. So A1 V1 Vf1 is equal to A2 Vf2. Clear? So put the value pi D1 B1 Vf1 is equal to pi D2 V2 B2 Vf2. So ultimately this is your equation, and B2 you have to find out all this value, it is given. So 400 mm is the answer. Clear? So I think it is clear. Now come to the very important point for your exam point of view. This type of problem you may see in your exam. So first of all, go through the problem. An inward flow reaction turbine has the external diameter and internal diameter 0.9 and 0.45. So internal diameter, external diameter is given. The turbine is running at 200, that means your rpm is given 200 rpm, and width of the turbine at the inlet is 200. B1 is given, inlet 200 mm. The velocity of flow through the runner is constant and is equal to 1.8 meter per second. Vf1 is equal to Vf2 given. The guide blade makes an angle of 10 degree, that means this alpha guide blade, alpha is given 10 degree, and outlet velocity 10 degree to the tangent of the wheel, and the discharge at the outlet of the turbine is radial. Very important point. And the discharge at the turbine outlet is radial, means at the turbine outlet the discharge is radial, that means beta is equal to 90 degree. Clear? So that is why VW2 will be 0. Okay, so the question basically itself giving us the information what we, that means how we can find draw the velocity triangle. So radial means at the outlet discharge, your radial means it is coming through towards the center. So that is why beta is equal to, you have to consider 90 degree, and as beta is equal to 90 degree, VW2 will be 0 automatically. Now you have to calculate what? Draw the inlet and outlet velocity triangle. Okay, fine. Find out number 1 absolute velocity of the water at inlet of runner. What you need to find out? Absolute velocity of the water, that means V1, that is the water velocity at which the water is coming out from the nozzle. Now absolute velocity of the jet you have to find out. Next, number 2, velocity of the reel at inlet VW1 you have to find out, reel velocity. Next, the relative velocity at inlet VR1 you have to find out. The runner blade angle you have to find out, that means theta and phi, these are the runner blade angle which you have to find out, we need to find out. Okay, now number 5, width of the turbine and outlet B2 you have to find out. Clear? Number 6, mass of water flowing through the runner per second, that means mass flow rate, mass of water flowing through runner per second, we know the rho into q. Okay, mass flow rate. Anything else? Okay, number 7, head at the inlet of the turbine. Head at the inlet of the turbine means, head means we know that it is equal to 1 by g VW1 U1 plus minus VW2 U2 plus V2 square by 2g, because kinetic head and work done per unit weight, that is the head at the inlet, because this head is converted into shaft work or what is the work done, and the kinetic head at the outlet. Okay, next, power develop and hydraulic efficiency of the turbine. You know that power develop, you can find out the power also 1 by g, not 1 by g, it is your mass flow rate rho q VW1 U1 plus minus VW2 U2 by 1000, that is your in terms of kilowatt you will be getting. And efficiency, hydraulic efficiency, you know, output by input, this is your output, input is your kinetic energy, half mv square. Okay, ultimately, so let us solve the numerical. These are the given data, you know, and u1 you can, as the n is given, d1 is given, so you can find out u1 is equal to pi d1 n by 60. So the answer is this 9.4 and u2 is equal to 4.7 meter per second. Now first question is your find out the absolute velocity of the jet at the inlet. So this is your velocity triangle, you can see the velocity triangle, this one is your absolute velocity of the jet, this one is your real velocity at the inlet, this is your this is your u1 velocity of the wheel at the inlet, this one is your alpha, this is your theta, this one is your vr1, this one is your vf1, this is your wheel, and in the wheel the vane, basically vane is adjusted, and this is your vr2, this one is your u2, only u2, and this is your vf2, also it is v2, and this one is your angle beta, and this one is your alpha phi, and as it is radially, so beta will be 90 degree. Now you can see here this is your tangent, so with respect to the center point, this makes an angle 90 degree. Here again it is your 90 degree. Clear? So it is your inward radial flow reaction turbine. So you can see outward to inward water is flowing. Now from this diagram, what you need to find out? V1. And V1, how we can find out? We know that Vf1 is equal to what? Vf1 is equal to, this is your perpendicular, so hypotenuse into sin alpha, so V1 sin alpha, alpha given, Vf1 given, so you can find out V1. Clear? Vw1, how we can find out? We know that VW1 is equal to V1 cos alpha, isn't it? VW1 is equal to V1 cos alpha. Alpha given, V1 given, you can find out VW1. Am I right? Now how we can find out the R1? So you know that from the triangle like this VF1 is given, V1 given, VW1 given, isn't it? Theta you need to find out, alpha is given. So V1 you know, VW1 you know, this U1 also you know. Okay. Now if this side you know and this total you know, also this U1 also know. So what we can write? Tan theta is equal to VF1 by VW1 minus U1. Can I write this? Now from this equation you can find out easily theta. Can I write this? Okay, theta you can find out, because theta is equal to tan inverse VF1 by VW1 minus U1. Again, what I need to find out? Why I need to find out VR1 also. So VR1 square is equal to VF1 square plus VW1 minus U1 whole square. Can I write this? So from this equation VR1 can be found out. Okay, so I know VR1 right now, I know theta, I know VF1, I know VW1, I know U1, I know V1. Next you have to find out phi. So phi is equal to tan inverse what? VF2 by U2, isn't it? And you know that VF2 is already, VF2 means your VF1, so 1.8, and U2 also you have got, this is your U2 4.7. so phi you can find out easily. Clear? Anything else? So phi, and that means your runner blade angles you can find out. Velocity of reel at inlet already you have got, relative velocity you have got. Next, come to the next point, your point number 5. Point number 5 is your what? Width of the runner. You know that pi, continuity equation, Q is equal to area A1 V1 is equal to A2 V2 VF2. So continuity pi D1 B1 VF1 is equal to pi D2 B2 VF2. Now pi cancel out, VF1 V2 VF2 cancel out. So ultimately D1 you know, B1 you know, D2 you know, you can find out B2. Clear? So from this equation you can see here basically VR2, this is the equation, tan theta is this, tan theta and phi is this. So ultimately B2 is your D1 into B1 by D2. So ultimately 400 is the answer. Next, mass flow rate. Now how we can find out mass flow rate? Mass flow rate is equal to, we know that Q, mass flow rate is rho into Q. Am I right? And Q is equal to pi D1 B1 VF1. Now discharge you know rho density. Okay, rho into Q, mass is equal to rho and density is equal to 1000, and discharge already I have got this amount. This is your discharge, this is your discharge. Okay, meter cube per second. So ultimately 1017.8 kg per second, that is your mass flow rate. And VR2 1.9, theta is equal to 66.4 degree and phi is equal to 20.9 degree. This one B2 400. Clear? Now let us come to the last point, that is your head at the inlet of the turbine. Now head at the inlet of the turbine means total potential head, that means potential energy per unit weight. So potential energy per unit weight is your head. Now it is equal to what? It is basically converted into work done and the kinetic head which is available at the outlet of the turbine. So work done per unit weight is what? 1 by G VW1 U1 plus minus VW2 U2 plus kinetic head at the outlet V2 square by 2G, isn't it? So that is written here, you can say 1 by, as beta is your 90 degrees, so that is why it is your 1 by g VW1 U1. So put the value, you know all the values, put the value, will be getting the answer 9.97 meter. Clear? Last point number 8, question number 8, power develop is equal to work done per second by 1000. So rho q VW1 U1 by 1000, 97.9 kilowatt is the answer. And hydraulic efficiency, last one, you know that VW1 U1 by GA is, because why? Because we know that hydraulic efficiency output by input, and output is what? Output is equal to mass flow rate into VW1 U1 plus minus VW2 U2 by water power is what? W is by 1000, and it is by 1000 also. So 1000 cancel out. W is equal to mg. So m and m cancel out. So by GAs. So automatically here basically GAs will be remain, and here basically this part will be 0, as because VW2 is equal to 0. And why VW2 is equal to 0? Beta is your 90 degree. That is why it is coming VW1 U1 by GAs. Clear? So that is why hydraulic efficiency you can get 98.38%. That is the answer. So I think it is clear now. The next 18.16, this homework is given to you. Solve it in your home. Okay, and this is your assignment also. So whatever the assignment is given to you, send it to my official mail. Don't forget to see this lecture, and don't forget to write done in the comment section. That is your attendance, you know, as I told you earlier. And one more thing, if you are getting any kind of difficulties, any kind of query, any kind of problem, then ask me frequently, ask me question. I will solve it in your comment section, or either if I think that I have to make a video, special video, so there is a doubt clearing playlist in the doubt clearing section. Okay, so go through that part, you will see your answer. Okay, the answer will be displayed on the doubt clearing class. Okay, so this is today up to this. Thank you for listening. Jai